A soft, skin that can mimic the sense of touch. Receptors in human skin can sense the weight of a butterfly, the heat of a flame, or the coldness of a cool drink. Thanks to them, we can feel even a pulse, and only with a gentle touch. Engineers have long been developing materials that mimic this sense. Now, for the first time, they've created an e-skin that allows you to feel heat or pressure and communicate directly with your brain. Mechanoreceptors located in human skin are responsible for receiving mechanical stimuli, such as touch, vibration or stretching. An external stimulus changes the potential of the receptor membrane, which generates a nerve impulse reaching the central nervous system. Researchers at Stanford University have succeeded in developing soft integrated circuits that convert sensed pressure or temperature into electrical signals similar to nerve impulses. This allows the e-skin to communicate with the brain. Scientists hope that one day these signals can be directed to implanted chips in peripheral nerves. This technology could lead to the development of prosthetic limb coverings that mimic the sense of touch. It would give the users the ability to feel heat or pressure. It would help restore partial sensation to people whose skin has been damaged. Other potential applications include new implantable or wearable medical devices. Such an e-skin could also enrich virtual reality experiences. The discovery was published in the journal Science. We have been working on e-leather for some time. The main hurdle in the work was not so much finding mechanisms that mimic the extraordinary sensory abilities of human receptors, but combining them using only skin-like materials. Explains chemical engineering professor Zhenan Bao, lead author of the study. The researchers explain that the challenge was to perfect skin-like electronic materials so that they could be incorporated into complex integrated circuits that could generate impulses similar to nerve impulses. The material also had to have a low enough voltage to be used safely on the human body, says Weichen Wang, a PhD student at Bao's lab. Wang worked on the e-skin prototype for 3 years. Researchers therefore sought a soft IC that could mimic the mechanisms of sensory receptors and operate efficiently at low voltage. Wang's first attempts, however, required more than 30 volts or more and could not provide sufficient circuit functionality. The new e-skin operates at just 5 volts and can detect stimuli similar to real skin, explains Wang. Artificial skin will be crucial for the next generation of prosthetic limbs, which will not only be able to restore movement, but also partly the sense of touch. Most e-leather consists of multiple layers of materials that resemble real leather. Within each layer are organic nanostructures that transmit electrical signals. These networks can be designed to sense pressure, temperature, stress and chemicals. Each such layer has its own integrated circuit. 6 similar sensory layers are then combined into a uniform material that does not delaminate, tear or lose electrical function. The finished material is no thicker than a micron, but it is too thin a layer to be handled easily. So we use a special substrate, which increases the thickness of our e-skin to about 25 to 50 microns. That's about the thickness of a sheet of paper. Human skin has a similar thickness, explains Professor Bao. It is the first material that combines all desirable electrical and mechanical characteristics of human skin in a soft, durable form and can be used in next-generation prosthetic skins. Thanks to it, scientists hope to develop innovative human-machine interfaces that could provide the sense of touch to people with prosthetic limbs. The eyes of the dead reacted to the light. Scientists have brought photosensitive cells back to life. Scientists have revived the light-sensitive neurons in the eyes of post-mortem organ donors and restored communication between them. This is part of a larger series of experiments that could transform brain and vision research. These studies also offer new opportunities in transplantology and question the irreversible nature of death. Billions of neurons in the central nervous system transmit sensory information in the form of electrical signals. In the eye, specialized neurons called photoreceptors sense light. A team of scientists from the Ophthalmology Center of John A. Moran at the University of Utah and researchers at Scripps Research used the retina to study how neurons die. They also tested new methods of reviving them. We were able to awaken the photoreceptor cells in the human macula, which is the part of the retina responsible for central vision and the ability to see fine details and colors, explains Dr. Fatima Abbas of the Moran Eye Center, lead author of the study. In eyes taken up to 5 hours after the donor's death, these cells responded to bright light, colored light, and even very faint flashes, he explains. An article describing the research was published in the journal Nature. While initial experiments allowed the photoreceptors to be revived, it turned out that the cells had lost the ability to communicate with other cells in the retina. The team identified oxygen deprivation as the most important factor leading to this loss of communication. To solve this problem, Professor Anne Hanneken obtained the donor's eyes less than 20 minutes after death, and Dr. Franz Winberg designed a special device that restored oxygen and other nutrients to the donor's eyes. Winberg also constructed a device to stimulate the retina and measure the electrical activity of its cells. Thanks to this team, they were able to recreate a specific electrical signal found in living eyes, the B wave. This is the first B wave record from the human retina after the patient's death. We were able to get the cells of the retina to talk to each other the way they do in the living eye, mediating human vision, says Winberg. Previous studies have restored very limited electrical activity in the eyes of organ donors. But this has never been achieved in the macula to the extent that we have now demonstrated, emphasizes the scientist. The process demonstrated by the team can be used to study other neural tissues in the central nervous system. This is a groundbreaking technical advance that could help scientists better understand neurodegenerative diseases, including retinal diseases such as age-related macular degeneration. Winberg points out that studies on eyes taken from the dead are qualitatively better than those performed on animals. Although mice are commonly used in vision research, they do not have a macula. Researchers can also test potential new therapies on functioning human eye cells, speeding drug development. The scientific community can now study human vision in a way that is not possible with laboratory animals, says Winberg. We hope this will motivate organ donor associations to understand the new and exciting opportunities that this type of research offers, he emphasizes. And these new possibilities are really exciting. The researcher's achievement is of great importance in transplantology. While organs such as kidneys or liver can be stored for many hours from the moment of collection from the donor, the tissue from the central nervous system dies almost together with the person. Restoring eye function after donor death gives new hope to all those waiting for a transplant. Hanneken, who is also an experienced eye surgeon affiliated with Scripps Memorial Hospital La Jolla, said the ability to produce viable patches of human retinal tissue could accelerate the development of new treatments for diseases that cause blindness. Until now, It has not been possible to make harvested cells from all layers of the retina communicate with each other in the way they do in a living retina, says Hanneken. However, in the future, we may be able to use this approach to develop treatments to improve vision in people suffering from macular diseases such as age-related macular degeneration, he explains. New footage from the ruins of the nuclear power plant in Fukushima. A few days ago, a remote-controlled underwater robot was sent to flooded rooms at the tsunami-damaged Fukushima Daiichi power plant in Japan. The recordings managed to capture images of molten fuel located in the cloudy depths of the reactor. The Fukushima nuclear disaster occurred on March 11, 2011. 3 reactors at the Fukushima nuclear power plant in northeastern Japan catastrophically melted after an earthquake and a 15-meter-high tsunami. It was the worst nuclear disaster since Chernobyl in 1986. Due to the harmful radioactive isotopes that have been scattered around the area, nearly 160,000 people have lost their lives. Residents were immediately evacuated, and the Japanese authorities introduced a 30-kilometer exclusion zone around the power plant. When the disaster happened, Units 1, 2 and 3 were operating. And there was fuel in the reactors. The tsunami destroyed the power sources and cooling systems used to control the temperature of the fuel, releasing a tremendous amount of heat that melted both the reactor and the fuel. Eventually, this melting slurry of fuel and equipment cooled and solidified into radioactive debris. Engineers are now figuring out how to remove them. The purpose of a recent mission was to obtain information about the main tank of reactor number 1, as well as to locate the molten nuclear fuel, which remains submerged in highly radioactive water to this day. The engineering team plans to remove all the radioactive debris. For this reason, the current mission of a small, remotely controlled submarine studied their sizes and analyzed the emitted isotopes. Robots are used for the work, because the level of radiation in the depths of the power plant is too dangerous for humans. As reported by the Associated Press, in some places the radiation level is 2 sieverts, SV, which is a lethal dose of ionizing radiation for a human being. With the help of an underwater robotic camera, the team installed special homing rings that will help guide future probes. The camera also managed to capture images of the nuclear fuel that had melted and sank to the bottom of the damaged reactor. TEPCO, along with the International Research Institute for Nuclear Decommissioning, IRID, and Hitachi GE Nuclear Energy, are to clean up and decommission the plant. Some of the activities will be aimed at removing the physical debris, but there is also the problem of highly radioactive water that flooded the power plant. In the aftermath of the disaster, melted fuel residues got into the concrete bases of the reactor buildings. Since then, workers have been pumping water there to prevent the rubble from overheating and causing further damage. All the contaminated water was collected in one place and now fills more than 1,000 steel tanks at the Fukushima power plant site. Authorities in Tokyo plan to dump some of this contaminated water into the Pacific Ocean, although the idea has sparked controversy and has met with opposition from environmental groups, local fishermen and neighboring countries. The government's advisory committee, which included representatives of science and people representing the interests of citizens, noted in a statement that the only practical option to remove the problematic water is discharge into the sea. It was also noted that other nuclear power plants had previously used similar practices, with minimal environmental impact. The coolant currently contained in steel tanks has been passed through a complex chain of filters. This purification captures 62 types of radionuclides, but not tritium, a radioactive isotope of hydrogen that occurs naturally in trace amounts in seawater and the atmosphere. Tritium is extremely difficult to remove because it replaces the hydrogen atoms in water molecules. However, tritium emits only beta radiation, which is less penetrating than alpha radiation, and therefore poses little health risk. The plan is to dilute the water until the concentration of tritium reaches 1/40th of what is allowed by Japanese authorities in drinking water. All in all, the entire process of decommissioning the power plant is to be completed in 30 to 40 years.